Hi Year 10, let's have a look at your section 2, so your written questions this time. So question 1 looks at two blocks A and B, and they're joined by a thin thread that passes over a frictionless pulley. Okay, so no energy is lost as this turns because it's frictionless. So block A is at rest, not moving, on a rough horizontal surface, and block B is held at rest just below the pulley. So we can see that when this is released, the thread will unravel and become taut. Block B will be released and then it falls vertically. And the thread is loose, so there's no tension in the thread until block B moves down by 0.45 meters, at which point the thread is then going to be straight. There's going to be tension in there. The mass of the block B is 0.5 kilograms, and in part A, it's pretty straightforward. It just says calculate the change in gravitational potential energy of block B as it falls through 0.5 meters. So this is mg delta h, where m is the mass, which was 0.5, g is always 10, and the height difference is 0.45 meters. 1 mark for the equation, 1 mark for getting the correct answer, which is 2.25 joules. In B, it says the mass of block A is 2 kilograms. When the thread tightens, it pulls on block A, which moves to the right at a speed of 0.6 meters per second. Calculate the impulse, which is the change in momentum, exerted on block A as it accelerates from rest, so U is 0, to 0.6 meters per second, which is V. So you just needed to remember that the impulse equation, which means change in momentum, is the final momentum, m multiplied by v, minus the initial momentum, mu, that got you 1 mark. And then it was plugging the numbers in, so m was 2 kilograms, v was the final speed, which was 0.6, and u was the initial, it was at rest, so it was 0. So we're just doing 2 multiplied by 0.6 gets me 1.2 Newton seconds. So 1 mark for remembering the impulse equation, 1 mark for the correct sum, and 1 mark for your final answer there. In question 2, a force is a vector quantity. State 2 features of a vector quantity, so you just need to say that it has a size and it has a direction, 1 mark for each. State the names of 2 other quantities that are vectors. So I have listed 7 by the looks of things. But that's just so I can show you the options. If it tells you to only give 2, you must only give 2 or you will lose marks. You don't want the examiner to have to choose the right answer for you. So I will dock a mark if you've listed 3 of them. But these are your options for vectors other than force. So acceleration, gravitational field strength, which is G, impulse and momentum I've categorized together because they're both momentum values. Velocity, weight, displacement. Weight was allowed on the mark scheme, but that's a bit iffy. I wouldn't choose that one purely because it's already listed that forces are vectors and weight is actually just a specific example of a force. So that's your worst option in my opinion, and it's possible that in future years they wouldn't allow that. So then it says a student suspends a spring from a clamp stand and measures the length of the spring. So you've seen this equipment before. The student then suspends loads of different weights from the spring and measures the length of the spring for each load. He then plots a graph of the length of the spring against weight. And then you've got a figure 2.2 as the graph that the student has plotted. So we can see the graph here. So as we add weight, we can see that the length of the spring increases. So it says, for the first part, using figure 2.2, determine the initial length L0 of the spring. Well, obviously the initial length is going to be when no weight is applied, so that's going to be when weight is 0. And when weight is 0, our length of our spring is 6 squares up out of 10. Each of these small squares is worth 0.02. I know that because there are 10 squares here. There are 10 squares between 0 and 0.2. So I'm just dividing that by 10. I know that I've got 6 of those 0.02s. So multiply those together and I get 0.12 meters. So that's my original length of the spring. In part II, it says state what is meant by the limit of proportionality That's 1 mark. And using figure 2.2, determine the weight of the load that causes this spring just to reach the limit of proportionality. So firstly, the first mark, well, the limit of proportionality is the point on the graph where the extension is no longer proportional to the force. So what I've done is I've gone to my graph. Let me just grab a ruler. Pop my ruler down and look at where the line deviates away. So I can see at this point, I no longer have the line along the ruler and it deviates away. So I've reached my limit of proportionality at this point. So then I just track down at that point, and that's 10.8 newtons that it is equivalent to when you read the scale. So therefore, it must be that the limit of proportionality is when the weight is 10.8 newtons. So then using figure 2.2, determine the spring constant of this spring. Okay, so firstly we needed to remember the equation F equals kx. Then we rearrange because what we're looking for is the spring constant, which is k. K is F divided by x, okay? And I'm going to basically take that from the graph. So you could find the gradient, but the gradient is actually the length divided by the weight, so you would have to flip it. So the easiest thing to do is, because you know that it should be a direct proportionality, you can take 2 of the points. So I chose 8 newtons. And when I had a weight of 8 newtons, I found that my length of my spring was 0.46. So I'm going to pop that on there just in case we need to refer back to it. Okay, so I said when weight was 8 newtons, the length was 0.46 meters. Now, what might have caught you out is that that is not your x value. X is the extension. We know that the original length of the spring was 0.12 meters. So the extension is just how much extra we've got. So we actually have to take that original length away. And that gives me the extension of 0.34 meters. Okay, so my length at 8 newtons minus the original length is the extension at 8 newtons. And now I can plug in for K, okay? And that gets me 23 newtons per meter. Now, there are multiple ways we could have got these values. I will, as long as your answer is right and you've done it in an acceptable way, I will allow. That's absolutely fine. You may not have done it in the same way as me. The range that you were allowed your K value to be between, based on reading the graph, was 22 to 25. So if you're out of that, you wouldn't have got the marks there. Okay, in question 3, figure 1 shows a tram. Trams carry passengers from one place to another. Helpful. A tram travels from A to E, stopping at B, C and D on the way. Figure 1.2 shows the speed time graph for this tram journey. So you can see that the speed of the tram is fluctuating over time. And so it says determine the time between the tram leaving A and arriving at C. So don't just read C as 10, because what you need to think about is the speed. The tram is travelling, and then as it approaches C, the velocity drops to 0 at this time here, okay? And then it stays at 0 through this time. If the velocity is 0 at this point, it must actually have arrived at C at this point. It dropped it to 0 velocity, so it stopped there. So it's actually at 9 minutes. Determine the maximum speed of the tram during the journey. So this is just a case of looking for your highest point on the graph, and that works out to be 7.5. It's halfway between 7 and 8 in meters per second. In part III, the tram decelerates as it approaches to each stop. Using the information from the figure to identify the greatest deceleration, give a reason for your answer by completing the sentence. So, the greatest deceleration occurs as the tram approaches, and we should have chosen C. The reason for this is the slope or the gradient of the graph is steepest in this section. So if we go back, we know that the gradient of a speed time graph is acceleration. So what we are looking for is when our graph is steepest. Now you can see that there is the biggest change in speed over the shortest time. That's only over 1 square, okay, from this section. In this case, this occurs over 2 squares on the x-axis, and it doesn't change by the same speed as this one. It's a smaller speed change. So this is going to be smaller than this one. So we can hopefully see that the biggest change occurred here over the shortest time here. So that was our biggest deceleration. Okay, and so to go back, you just needed to say the greatest deceleration occurs as the tram approaches C because the gradient is steepest in this section. The total distance between A and E is 5,200 metres. The tram takes 1,380 seconds to travel. Calculate the average speed. Well, average speed is just total distance divided by total time. The total distance was given here and the total time was given here. So just one divided by the other gets you 3.76 metres per second, or you could have given it to 2 significant figures. In question 4, this is a measurements question. So right at the start of the year, we discussed when we take measurements the need for repeats and to measure for multiple and finding averages. So that's what it's testing here. So a builder buys some tiles to repair a floor. He checks that the new tiles are the same size as the tiles on the floor. The dimensions are 25 by 20 by 0.3 centimetres. The new tiles are shown. That's a bit of a clue. They've given you a huge number of tiles to help you remember that n needs to be large. So the first bit was easy. State the name of a suitable instrument for measuring the length and width. A ruler, a metre ruler, a tape measure. One of those is fine. And then in part II for 3 marks, describe how to determine the average thickness of one new tile. Okay, so the word average tells us we have to have considered multiple tiles. So we place n tiles on top of each other. So n is a number, and you had to have n was greater or equal to 10 for them to consider it an okay number. So place 10 tiles on top of each other, or anything higher than 10. Measure the thickness of n tiles. So for instance, measure the thickness of 10 tiles. Divide this value by n, divide this value by 10 to find the thickness of 1. So you're basically saying stack an amount on top of each other, measure the thickness of the whole amount, divide by the number you stacked to find the thickness of 1 for each mark there. In part B, you're first asked to find the volume of the tile. It's a regular cuboid essentially, isn't it? Because you've got the tile shape itself and then a thickness. So, sorry, not very good at drawing here. We're doing this dimension multiplied by this dimension multiplied by this dimension. So we just multiply them all together and we get 150 centimetres cubed. Calculate the density of the tile, include the unit in your answer. This one's worth 4 marks. This is a gift of a question because it's a really easy calculation. 1 for remembering that density is mass divided by volume. 1 for plugging the numbers in correctly. 1 for the value being correct, and 1 for the unit being correct. And so we should have just done 410 divided by the volume that we got in the previous part. And then in part III, again, 3 marks for this is really a gift. W equals mg, weight is mass times gravity, but we have to remember that the mass is in kilograms. So 1 mark for the equation, 1 mark for converting to kilograms, 1 mark for the correct answer there. In question 5, table 3.1 contains incomplete information about the energy input and the useful output energy for a number of devices. The table is only complete for the microphone. Complete the table by writing in each blank space. So for each blank space that you got right, you got 1 mark. So for an electric fire, electrical energy is transferred to thermal energy. The whole point is it's a fire to warm us up. A wind turbine, the input energy, air passes through the turbine and makes the turbine spin. It's therefore moving. It has kinetic energy. It is used to create electrical energy. And then the third one was thinking of a device that transfers electrical energy to sound energy. So these are all possibilities for you here. You could have said buzzer, headphones, a bell, earbuds, something like that. AirPods would probably get you a mark these days. Loudspeaker, anything like that is absolutely fine. In B, a tennis player hits a ball over the net and it bounces as shown. Complete the sentences about the energy transfers. So, when the player swings the tennis racket, his body converts chemical energy to kinetic energy. These are just ones you need to remember, the energy types and stores. 2, when the tennis ball is moving upwards, the ball gains gravitational potential energy. I think you would have got away with just saying potential there, but be careful because some years you don't. In II, explain why the height gained by the ball decreases with each successive bounce. Energy is transferred to heat or thermal energy during contact with the ground, or you could potentially have said some sound energy is transferred to the surroundings as well. Okay, question 6. Ignore the doodles for now. So during an experiment, a heater supplies thermal energy to a substance. Initially, the substance is a solid. The substance is heated until it becomes a gas. The temperature of the substance varies with time, as shown in figure 4.1. Okay, so we've got a graph where we can see over time the temperature is rising steadily, then it stays constant during A, rises again, stays constant during B, rises again. Give the state of the substance between A and B. So we hopefully know that in terms of temperature, we find that a gas will be at a higher temperature than a liquid or a solid. So you should have remembered that during this section, this is a liquid. And then state the process. So from solid to turn to a liquid, that's melting. And then from liquid to turn to a gas, that's boiling. So this one should have been pretty straightforward. Liquid, melting, and boiling. This next bit is not so straightforward. So the experiment is repeated using a heater with a greater power output. Highlight the key words. That tells me that there is more energy transferred per second. Okay, that means that the heat energy is going to be transferred into the substance and the kinetic energy is going to increase quicker. Okay, we know that temperature is a measure of the average kinetic energy of the particles. So if the average kinetic energy has increased at a faster rate, the temperature is also going to increase at a faster rate. Suggest how the temperature of the substance varies with time by drawing on figure 4.1. So, key things to remember. Melting and boiling temperatures are fixed for a substance. Okay, so for example, ice will melt at 0 and water will boil at 100 degrees Celsius. Those are fixed temperatures. They do not change. And for that reason, wherever I have melting and boiling in my new graph, they have to be at the temperature that we already had previously. Okay, so those lines need to be along the same value. We still have to have all three phases of matter, so we still need solids, liquids and gas, but we know that there is a quicker process happening for us to reach a gas temperature quicker, because we just saw that the power input is greater, which means that the energy transfer is greater, which means that the temperature rises more quickly. Okay, so all we do is we reach that temperature in a quicker time, so we just shorten the time, so we have a steeper gradient. Then we melt. Remember, the melting time will also decrease because we are giving more energy per second during this process. So you just need a steeper line for the first section, a shorter line for the A section, a steeper line again for my liquid section, a shorter line but at the same temperature for B, and then steeper. So it's just basically showing that the temperature increases more quickly and the temperature at which melting and boiling happens is the same, but it will take less time. So your graph should have looked like the orange one here. Last but not least, in C, this should have been quite a nice one, I hope. Describe the arrangement and movement of the molecules in a solid and in a gas. Write your answer in the table. So for a solid, the arrangement of molecules is 1 mark for each box. You should have said they are close together in a regular structure. For a gas, they are far apart. They are in a random arrangement. The movement of molecules in a solid is that they vibrate around their fixed positions, and for a gas, there is completely random movement and collisions. So there you go.